Alright, so yesterday we discussed Rhodric formula. This formula in fact provides a necessary and sufficient condition for a given direction to be an asymptotic direction. Okay. So in terms of lines of curvature, in fact principal direction, sorry, in terms of lines of curvature, we can put the condition as a curve C. I am stating the same condition. So, a curve C is on a surface is a line of curvature if and only if this condition d n plus k dr equal to 0. Yesterday, I said the same condition in terms of principal directions, because what happens is, if you look at a curve over a surface, if at every point the tangent is in the direction of principal direction, then the curve is said to be a line of curvature. So, the same statement can be written in terms of the line of curvature as follows: d n plus k n d r equal to 0, where k n is the normal curvature. Since this is the normal curvature which is considered over a line of curvature, so the principal curvature and the normal curvature are same. If I say k n is a normal curvature or I say it is a principal curvature, it is the same as long as your curve is a line of curvature. Is it right? So, somewhere you will notice that the statement is written like this. So, this is what the Rhodric formula is. This formula in the box is called the Rhodric formula. All right. Now, using this we can solve some exercises. So, one of the exercises is parametric curves on a surface of revolution. Parametric curves on a surface of revolution. Or its line of curvature, or its lines of curvature. This is the statement, show that. In order to address this problem, we have to see that in general, when does the parametric curves becomes lines of curvature, or the lines of curvature are parametric curves. There is a condition, the lines of curvature are parametric curve if and only if G12 and B12 both are 0. So, what we will see in this case of surface of revolution, what about G12 and B12? If you find that they are 0, your statement is proved. So, if you remember it is given by f u cos v, f u sin v and h u. So, this is how we write down the parametric equation of a surface of revolution. So, we need to compute G12 and B12. We have already seen somewhere that G12 is 0, but anyway let us work them out again. So, this is f dash into cos v, f dash into sin v, and this is h dash, and then R 2 means derivative with respect to v. So, minus f sin v, f cos v 0. And from these two, you will see that G12, which is R1 dot R2, R1 dot R2 you can straight away see it is minus time f f dash sin v cos v plus f to f dash sin v cos v, and this product is 0. So, you can see that G12 is straight away 0. For B12 I need to compute n. N I can consider the cross product of R1 and R2, that will be 0 minus f h dash. So, minus f into h dash cos v, okay, then minus 0 f h dash sin v, and then f f dash cos square v plus f f dash sin square v. So, this is simply f f dash. You are interested in modulus of this vector also, that will be f square into h dash square cos square v. So, plus f into h dash square sin square v. So, this is simply f square h dash square and plus f square into f dash square. This is the modulus. You can take f common. So, this is f dash square plus h dash square. F you can take common from here also, and that will be cancelled out from the term in the denominator. You will be getting here this is square root. This is the unit normal of the surface of revolution. Okay. Now, for Bij's, I need to compute further derivatives of R1 and R2. So, that is R11 means derivative of R1 with respect to u. So, that will give you f double dash cos v, f double dash sin v, and h double dash, and R22 if you see, so derivative of R2 with respect to v. So, that will be minus f cos v, okay, and minus f sin v and 0. And B11 you can see directly. So, B11, in fact, I do not need to compute B11 and B22, you just need B12. So, I have to write down R12 also. R12 means I have to differentiate R1 with respect to V. So, that must be minus f dash sin V, and this will be f dash cos V, and this one is 0. Now, n dot R1 2. So, B12 is n dot R12. Both are available to us. This is R12 and here you have n. So, you can see from here itself what is happening. So, it is f dash h dash sin v cos v, and then again you have f dash h dash sin v cos v, and the last product will be 0. So, straight away it is 0. So, you have seen that both G12 is 0. So, we have G12 equal to 0 and which is also B12 0. So, now using the theorem which says that asymptotic lines of curvature are parametric curves if and only if these two things are 0. So, this proves the assertion. Okay, so, whenever you are given problem like this, you need to think of the characterization. So, can you apply characterization to prove the assertion? Here we could use the characterization. Then we discuss the idea of asymptotic direction and asymptotic curves, asymptotic lines rather. So, this is what we discuss, asymptotic directions and asymptotic curves, asymptotic lines rather. Asymptotic lines are those lines, sorry, asymptotic directions are the directions DUIs such that the second fundamental form along this is 0, and a curve whose tangent at every point is along the asymptotic direction, we call it an asymptotic line. Okay. So, this is the definition which I stated in my last lecture. Now, the condition that becomes or characterization for a curve to be an asymptotic line is that its second fundamental form is identically 0, or you can say that B11 into du1 square plus 2 times B12 du1 du2 plus B22 du2 square equal to 0. This is a differential equation. We call it a differential equation for asymptotic lines over a given surface. All right, now there are some easy observation. One of the simple observation is that along an asymptotic line the normal curvature will be 0, and this follows from the formula of the normal curvature. It is in fact Bij dui duj upon Gij dui duj. So, since Bij duj duj is 0, it must be Kn must be 0. So, that was straightforward. So, this happens on an asymptotic line. We have some other observations regarding asymptotic lines. When does parametric curves become asymptotic lines? So, parametric curves are asymptotic line. This is observation number 1. Number 2 was parametric curves are asymptotic lines if and only if we just use this fact somewhere, B11 is 0 as well as B22 is 0. All right, this fact is also necessary and sufficient both. So, somewhere if you are asked to show that the parametric curves are asymptotic line or asymptotic lines are parametric curve, you can use this characterization. Okay. There are some other observations. Suppose I have a surface on which I can draw a straight line. There are many surfaces, for example, a cone you can draw a straight line, a cylinder you can draw a straight line. So, what about these straight lines? So, whenever a surface admits a straight line as its part, it will always be an asymptotic line. Okay. So, straight lines on a surface are asymptotic lines. So, this is a fact which you can easily prove. No, we did do.
So, either asymptotic lines are straight line or
yes, this is a more general statement, but if I give you, suppose you have a surface. Suppose you have a surface on which a straight line is drawn, whether this straight line is a asymptotic line or not, when how you will prove? Asymptotic lines may be straight line or something else may happen, but the other way around. So, this is an observation, you may call it a theorem or something. Straight lines on a surface are asymptotic line are this fact we have to prove. So, suppose I have a surface sigma with parametric equation this, and suppose there is a line L which is drawn over this surface sigma, and its parametric equation is something r equal to r s. I have to show this L is a asymptotic line. So, how would you show it? So, look, suppose n always denotes a unit normal. So, I will look at this n dot t will always be 0, because t is a tangent to the curve L and n is normal to the surface. So, the dot product of the two will always be 0, because they are always orthogonal. So, as n dot t equal to 0, we by differentiating it. So, on differentiating this with respect to s, I will be getting n dash dot t plus n dot t dash equal to 0. So, or I can say n dot t, okay, n dash dot t plus n dot t dash is k n, k n equal to 0. Now, in the second term, since the curve is a straight line, curvature will be 0. So, this is 0 because the curve is a straight line. The curve is a straight line. So, what do you get is, this implies n dash dot t equal to 0, which means n dash is a vector which is perpendicular to t. Okay, since it is also perpendicular to, in fact, or I can say here n dash I can write down as d n. Okay. So, since and this means d n dot t, and t I can write down as d r, is it right? So, this means d n dot d r equal to 0. When d n dot d r equal to 0, if you remember yesterday I was saying that the second fundamental form is 0 if and only if d n dot d r is 0. So, that means this implies the second fundamental form is 0, okay, and second fundamental form is 0 along a curve, then the curve is a asymptotic line. This implies L is a straight line, sorry, asymptotic line. Its generalized version I discussed in my last lecture. In fact, whatever asymptotic line you choose, you will see either it is a whatever asymptotic curve you see on a surface, either it will be a straight line or its oscillating plane will be a tangent plane. So, this I had done earlier. So, more generally we have that theorem. More generally we have theorem, perhaps it was number 2 or 3, I do not remember, you just write down the number. All right. Okay. Next.
So, direct means we can use the result whenever in surface straight line it is asymptotic line.
Yes, whenever you have a surface on which you can draw a line, that line, straight line I mean,
Yes.
it will always be a straight line. Okay. Asymptotic line. Okay, now look at the second case. So, this theorem in fact, if I recollect, so an asymptotic line is either a straight line or its osculating plane is tangent plane. This was the statement. Okay. Now, if you know an asymptotic line which is not a straight line, then you would like to see its curvature and torsion. So, if a asymptotic line is not a straight line, then its torsion and curvature are related. So, this is the next theorem. If an asymptotic line on a surface is not a straight line, its torsion and curvature, definitely it will have some curvature and torsion as well. So, its torsion and curvature satisfy the following relation: tau square plus k will be 0. Okay. So, that is the relationship between curvature and torsion. All right. So, proof. So, if the unit normal is being denoted by capital N. So, we have from the earlier observation that n dot n is 0. We know that along the asymptotic line, an asymptotic line yes. Yes, n dot n is 0. N dot n is 0. Okay. And now, if I differentiate it, so differentiating this will give me n dash dot n plus n dot n dash equal to 0. Okay. N dash is tau n, no, tau b minus k t. N dash is okay. Don't differentiate it and see it won't give you anything. We also have n dot t equal to 0. Also, we have n dot t equal to 0. Yes. So, this implies that n is orthogonal to the osculating plane. Osculating plane is made up of small n and small t. Or it also implies that n is parallel to the binormal of the curve. Curve is the asymptotic line, or you can say that n equal to, both are unit vectors. So, I can say it is plus minus p. Okay. So, this implies that n dash or dn over ds, whatever you call it, dn over ds, dn over ds will be equal to plus minus dv upon ds. Now, dv upon ds is minus tau n. So, this will give you plus minus tau n. Okay. Now, dn dot ds. So, n dot n will be what? dn dot dn. So, if I consider dn upon ds dot dn upon ds, I am taking dot product. So, this will be tau square. Okay, n dot n is 1. So, it is simply tau square. Now, as a consequence of Rhodric formula, we had obtained the following. So, as a corollary to the Rhodric formula, we obtained the following relation. If you remember, dn dot dn plus m times dn dot dr plus k times, this is Gaussian curvature, dr dot dr equal to 0. This was the formula? Okay. Now, dn dot dn I have as tau. So, this is tau square. In fact, into ds square also. Okay. And dn dot dr will be 0. Why? Because dr is t. And in fact, dn dot dr come out to be the second fundamental form. Okay. And since your, so this will become 0. So, second term is 0. And k times dr dot dr I can write down as ds square. All these things are known to you. Okay. So, what you have is, sorry, k times. So, or I can say that tau square plus k into ds square equal to 0. Arc length cannot be 0. So, from here tau square plus k equal to 0. This is what you wanted to show. Okay. So, if a asymptotic line is not straight, it is a curved one. So, the curvature and torsion are related like this. Tau square is in fact equal to minus times k. All right. All right. Now, we have few more exercise. For example, lines of curvature bisect the angle between the asymptotic lines. This is another exercise. Lines of curvature show that, in fact, show that lines of curvature. This is interesting. Bisect the angle. Bisect the angle between the asymptotic line, between asymptotic lines. Okay, so suppose you have asymptotic lines like this. This is the first asymptotic line. I will call it asymptotic 1, and this is the second asymptotic line. let me call it asymptotic line number 2, and then there a line of curvature will bisect the angle between the two. So, if there passes a line of curvature between these two asymptotic lines, then this will bisect the angle. So, you draw tangents. So, this angle and this angle are same. All right. So, for convenience, once again for computation point of view, we can regard these asymptotic line 1 and 2 as the parametric curves over the surface. So, assume for the solution, let me assume that the asymptotic lines are parametric curves. When asymptotic lines become parametric curves, so what happens? So, in this case what will happen? In this case you have B 11 and B 22 both become 0. Okay. Now, you know the differential equation of the this curve C, let me call it, this is the curve C, which is in fact a line of curvature. This is a line of curvature. Okay. So, if you recall the equation of lines of curvature, so equation of lines of curvature, that is a differential equation of the type du2 square minus du1 du2, and then you have du1 square equal to 0. In the first row you have G11, second row rather, G12 and G22. Here you have B11, B12 and B22. Now, parametric curves coincide with the asymptotic lines. So, these two terms, this is 0 in our case as well as this is 0 in our case. So, if these two terms become 0, the equation of lines of curvature will become simpler, or I can rewrite it as du2 square into what? 0 into minus times B12 into G22. Okay. And then minus plus du1 du2 into 0 0, and then plus du1 square into G11 B12 equal to 0. Okay, so, the equation becomes let me write down G11 into B12 du1 square minus G22 into B12 du2 square equal to 0. In fact, if you remember, we had solved one exercise while discussing the angle between curves over a surface. This was in fact the equation of a bisector. In fact, in that exercise we had written it like this. We usually call G11 E also, and this L and M. So, this is m Lm into du square minus this was EFG, and this is okay. So, yes, m gm into du 1 square this was, and this is du 2 square. So, this is the condition of the orthogonal bisector for a curve to be a bisector of the given family of curves. So, this is the condition. This is the condition for a curve to be a bisector of the given pair of curves. You can check it up. This is one of the exercises in that section. Okay. So, we can use any of the results also in proving our assertion. All right. Now, one can ask to find out asymptotic line on a surface of revolution. Okay. This I leave, some exercises should be done by the students also. Find asymptotic lines on a surface of revolution. And for simplicity, you can assume that your surface of revolution is u cos v, u sin v, and h z equal to some f u. Okay, so there is a differential equation for asymptotic line. So, you will be getting a differential equation for this surface of revolution. So, computation, you know how to carry out the computation. Now, the next article is about the conjugate directions. Okay, so how much time? In fact, I will just define what these directions are, and then I will take up some results and problems in my next lecture. So, we can continue 5-10 minutes more. So, next is the idea of conjugate lines, conjugate directions. Well, suppose you have a pair of directions, one direction, and when I say a pair of direction, in fact, a family of pairs you can draw like this. So, a direction dui, given a direction dui, a direction delta ui. Delta is also a symbol of differential operator. Given a direction delta ui is said to be conjugate, is said to be conjugate to, is said to be a conjugate direction, is said to be said to be the conjugate of dui, said to be the conjugate of direction of dui, if what happens, if the following condition is satisfied. The condition is dn dot delta r equal to 0. Okay. The given directions are differentials d, and the other direction, the conjugate one, is delta. So, d and delta both are differential operator. D is the differential operator along the first family of curves, and del is the direction of the other family of curves. Okay. So, this is the meaning of, if you expand it, so or I can rewrite it as dn, you know, this is ni dui, this is rj delta uj. When you will take the dot product, it will become like this, bij or b1 bij dui delta uj equal to 0. Okay. In the expanded notation, it can be rewritten as b11 into du1 delta u1 plus b12 du1 delta u2 plus du2 into delta u1 plus b22 du2 delta u2 equal to 0. So, this becomes a condition for two directions to be conjugate. In fact, if you look at these relations, any of them, you will notice that these are symmetric in d and delta. So, this relationship of conjugacy is a mutual relationship. So, if one direction is conjugate to other, the other is conjugate to the first one. So, this is a mutual relationship, and we would prefer to say that dui and delta ui are in fact conjugate to each other, because of the symmetry of the relations. Symmetry means you can interchange d and delta, there will be no difference on the relation. अगर आप d और delta को आपस में interchange कर दें तो it will remain the same. So, there will be no change in the relation. So, that is called a symmetry of the relationship. So, since the above relations are symmetric in d and delta, since the above relations are symmetric in d and delta, we say that the directions dui and delta ui are conjugate to each other. That is, the relation of conjugacy is a mutual relationship, it is not a one sided relationship. Okay. So, this is the definition and some simple results, and in fact, you have just seen that the second fundamental form vanishes along the asymptotic lines. So, these are asymptotic with regard to each other. Okay, it is not asymptotic in the absolute sense. So, one direction is asymptotic vis-a-vis the other one. Okay, so, this is a more general relationship. So, we will elaborate this idea more in my next lecture. We will take up some problems and results on conjugacy of the relationship. I stop at this point.